Thank you very much. And thanks to the organisers for inviting me to make this presentation. I'll introduce it by bringing us down to the southwest Pacific, where New Zealand straddles the Pacific Australia plate boundary zone, which has about 4 centimetres of plate motion across it. It's characterised by high seismicity, and in the centre of the country there's a transition from Hikurangi subduction into continental transpressive deformation in the South Island. There are 2 major cities in this area, the capital Wellington and Christchurch cities. And across the deformation zone through this area, which is more than 200 kilometres in width, there are many active faults that have been recognised in the landscape and offshore and submarine data. These have generally been characterised in a conventional empirical, characterised by earthquake source parameters, and together with a background seismicity model from historical earthquakes, they form the earthquake source component in the National Seismic Hazard Model published in 2012. Those inputs lead towards a range of hazard maps, such as this peak ground acceleration map at the 1,000-year return time, and this kind of information informs our national building codes. In the last 5 years, both Christchurch and Wellington have been rocked by damaging earthquakes. They include the 2010 to 12 Canterbury earthquake sequence and the 7 earthquakes 30 or 40 kilometres south of Wellington last year. And these events have raised the awareness of hidden active faults not previously recognised in the national models, but yet captured by the background seismicity model in terms of general ground shaking hazard. In this talk today I'm going to focus on 2 areas, and these are case studies for low slip rate faults hidden beneath coastal areas in major urban regions. Firstly, we'll look at the offshore extensions of the structures associated with the Canterbury earthquakes, and then we'll look at some work that we've been doing in Wellington City, right in the heart, not on the Seton earthquake sequence just to the south in Cook Strait, but right up in the centre of the city itself. So the Canterbury earthquake sequence extended in time for over 2 years, between late 2010 and 12. It was very costly, leading to 185 deaths, more than $30 billion of damage, which is a fairly significant impact on the New Zealand annual GDP. It started in the west with main shock rupture on thrust and the strike-slip-Greendale fault, and during the development of the earthquake sequence triggered a range of large aftershocks that progressively migrated towards the coast in the east, with the devastating February 2011 event causing most of the damage and all of the deaths in Christchurch City. In June there was another substantial aftershock in the coastal area, and then later in December 2011 there was yet another rupturing a reverse fault offshore in Pegasus Bay. Geodetic modelling suggests that at least 10 different faults have been captured in this earthquake sequence, and this leads to an understanding of complexity in the basement rocks that are hiding beneath the Canterbury Plains in the offshore Pegasus Bay area. The migration of these earthquakes towards the coastal area was the motivation for this study of the offshore region in Pegasus Bay, and we've utilised conventional oil company multi-channel seismic sections such as this panel here. We collected high-resolution multi-channel data ourselves with boomer seismic reflection profiles, and we utilised a background archive data set of 3.5 kHz profiles. These were tied to a coastal bore right down here at Christchurch City, providing us with some stratigraphic constraints on the sequence. Mapping of faults imaged in the seismic data reveal a very complex network of structure. This includes the structures mapped there in black, which are inactive Cretaceous and Paleogene normal faults, primarily dipping to the south, quite a complex array. Basement generally lies at about 1.5 kilometres beneath the seabed, but up to 3 kilometres in some of these Cretaceous graben that are shaded in green in here. And superimposed over this older deformation fabric through the area that almost certainly extends into the coastal Canterbury area is the swath of red coloured structures on here which have evidence for late Pleistocene deformation on them. And we see that we definitely know that extends onshore into the Canterbury area, and of course we've had that captured at the very southern edge of the feather edge of this in the Canterbury earthquake sequence. I'll illustrate here some examples of those active structures in the northern part of the bay. These are characterised by reactivation of the Cretaceous extensional fabric. These two sections are time sections with 6 times vertical exaggeration. This is the depth section here with no vertical to horizontal exaggeration. And you can see these beautiful examples here of quite classic textbook small strain inversion tectonics. Some faults are still hiding at the positions and the fault tips have not propagated up through the sequence, others have. And they drive fault propagation folds through the sequence with most of the structures blind. Deformation of this yellow horizon that's about 1 million years old suggests that we've got slip rates of the order of 0.1 to 0.3 millimetres a year on individual faults up in that area, and that's in generally good agreement with boomer sections and 3.5 kilohertz data from which we can measure vertical displacements of horizons that we've traced down to the borehole at Christchurch. So this is what we see more in the northern part of the area, and some of these faults reach up to 35 kilometres in length, ranging between 10 and that distance. We also see some evidence for faults with normal separation through the sedimentary sequence that are contemporaneous with those structures up in the north. And the logical explanation for these might be that they're actually dextral faults. And these structures, this particular example is right here in the bay. These are not particularly large faults and not as well mapped, but very analogous to the Ashley Fault, for example, directly onshore where there's been documented dextral slip on that fault, and somewhat similar to the Greendale Fault that ruptured. Further south towards Christchurch City itself, the February 11, June and December events ruptured, as I said, going offshore, and frankly there's not a lot of evidence down there for really substantial late Quaternary structures that have propagated up through the sequence and generated significant folds that are easily mapped. We can just see some evidence at the right in against the coast of the February 11 event, perhaps in here with lower folding in the Pliocene section, but that's really masked by quite a bit of gas and not a lot of deformation in the Quaternary. Some profiles down in here, we do see some evidence of faulting through the volcanics of Banks Peninsula, which is an old Miocene volcano, not active now. But quite frankly, there's not really a lot of evidence for substantial late Quaternary deformation in there, although the earthquake sequence has ruptured into that area, and we must be looking at faults with very low slip rates on them. If we consider the 2012 national model, which are these bold orange-coloured structures that we'd already captured in this offshore area, from this study we can now make revisions, of course, to this, add in some new structures that we've discovered in this area, and of course we have the earthquake sequence itself on structures that we know are seismogenic faults. So the pattern of deformation is now somewhat different. We've got structures in the north with slip rates, as I said, 0.1 to 0.3. These are going to generate upper 6s to 7 events with quite long recurrence intervals. And that is compatible with the lack of Holocene displacement on the marine sequence over the nose of those faults. Further south, we must have structures that have even lower slip rates again, less than 0.1 millimetres a year. So we have slip rates on these faults probably of the order of tens of thousands of years, and that is not inconsistent with some recent rockfall data suggesting large rockfalls in this area at about a 7,000-year return time. To capture those results from the Canterbury part of this talk, we clearly see widespread faulting. It's very insightful what the marine data is giving us in terms of understanding the earthquake sequence. We've got Cretaceous and Paleogene extensional faults with a superimposed array of compressional structures over that. These include oblique slip and possibly strike slip faults with reverse reactivation of the older structures, low slip rates, moderate to high earthquakes potential, and in terms of ongoing hazard, because of the low slip rates, these structures are really largely captured in the background model, at least at the 500-year return time, but quite clearly they're very significant in terms of stress triggering and fault interactions. So I'll now move to the second part of the presentation, and I'd like to present some data that we've recently made public underlying the harbour right in the inner part of Wellington City, which is my hometown. It's the capital of New Zealand with 400,000 residents. And until this recent work was completed, a very large number of basement faults were recognised through the area shown by these black lines, largely on the basis of topographic lineaments in the greywackies that are exposed throughout the area. These Mesozoic greywackies like Franciscan here. The red structures on these are major strike slip faults with 4 or 5 millimetres per year dextral slip rates on them, and those were the primary earthquake sources recognised in the area, in addition to the Hikurangi subduction zone that underlies Wellington 25 kilometres deep. A chance discovery of an active fault right in the inner part of the harbour in here led to an extensive study in the last couple of years. That included 2 different sets of boomer seismic reflection profiles collected in a grid specifically designed to study where this fault is, somewhere south of the Wellington fault trace along the back edge of the harbour. We have a borehole from this area in here, cored with a sonic drilling rig that penetrated the entire marine sequence into the colluvium underneath, and 3 sediment cores that we've also dated. And we've used radiocarbon dating methods to constrain the age of some of the marine sequence stratigraphy. We also have Kongsberg 3000, 3002 multi-beam data with a 0.5 metre resolution grid DEM to work with. This work's been largely funded actually by the insurance sector through the It's Our Fault program. Here are a couple of examples of boomer seismic sections over this fault which we've only newly discovered has been an active structure. Generally there are 2 sequences in this. One of them is the post-glacial marine mud that filled up the harbour in the last 10,000 years following marine incursion. Underlying that is a colluvium and fluvial sequence with this high reflectivity, and we've recognised this fault displacing the Holocene sediments by up to 7 metres of displacement in the Holocene section. Generally, there's really no surface trace of that fault hiding away under the Holocene mud, which has probably been the reason it's not been discovered in the past. As I said before, we used borehole data over here by the Wellington fault with dated samples coming from these to determine the ages of these Holocene reflectors within the post-glacial marine sediments. We've been able to map the position of that fault extending from east of the Westpac Trust Sports Stadium down into the inner reaches of the city where the fault appears to come ashore at the inner part of the harbour. This is a detail of that, and we've noticed that whilst we have a single fault trace extending down in here, we have some complexity of that immediately offshore in the inner part of the bay here, and one of these traces in fact lies potentially either right against or immediately under this $150 million development that's just recently been completed. Overall, we find that we've got uplift of this fault to the east. It's dipping to the east. It appears to be a reverse fault. We've got no evidence that it might be have any dextral displacement on it, but oblique slip is possible. It clearly seems to be related to the uplift of Mount Victoria, which is this hill here where we're seen on the right-hand side there. There is in fact a seafloor scarp about 1 metre high, but it's present only in the very southern area of the area where the post-glacial marine mud has not covered that up. Slip rates on this fault, by the way, extending along the section in here are of the order of about 0.6 plus or minus 0.3 millimetres per year based on a number of these Holocene reflector events. So we've got something potentially approaching half to a millimetre a year slip rates on this fault. Now, what do we know about its earthquake history? Well, I'll very briefly step away from Wellington, which is here, out into the Cook Strait area, and just introduce to you or refresh you on some work that we did on these large strike-slip faults in this area where we had very thick post-glacial sediments reaching 45 metres, and we did very detailed vertical displacement analyses on those faults to look for co-seismic increments of displacement. This is within a framework in which co-seismic displacement events would be recorded in vertical displacement profiles, and the record that you would get from that would vary depending on whether you fill to the top or have a regular growth sequence. What we do is we analyse the vertical displacement histories on all profiles, and we calculate statistically mean ages for events, displacements for events and recurrence intervals from that. And in that particular area, we've tested this model against some paleoseismic data on land, on 2 structures now. So we've applied these methods in Wellington Harbour to the Aotea fault that we've just recently discovered has been active. And we find on 7 profiles we have a fairly consistent vertical displacement history through that post-glacial marine sequence. And there are 2 significant steps in that. One of them is at about 6,000 to 6,200 years ago, when up to 2 metres of vertical displacement accrued on that fault. The second is at about 8,400 years, where another 4 metres of total accrual occurred on that fault. Now, these represent minimum earthquakes when we ignited that phase of growth stratigraphy on that structure. Okay. It's quite possible that there's a third event recorded on one of these profiles, and of course we can't actually decipher any better resolution on these growth parts of this sequence than what we've got here. So it's quite feasible that there are other events that we haven't recognised or been able to detect in the data. Of course that would have some impact on the recurrence intervals on this fault. So what can we say about the earthquake potential on this, and where does the fault go? We only mapped the 2 kilometre trace of that, but we know we've got surface rupture on the fault. So if we consider empirical relationships using crustal earthquakes from the New Zealand national model, we need a structure at least 10 kilometres long to generate surface displacement for a start. And this fault does not join with the Wellington fault in the north. It peters out and stops, and it must project onshore, and it must reach the south coast to have anywhere near like the fault length required to generate the co-seismic displacements that we've seen in this data. Unless we're missing a lot of events, if we want to capture 2 metre displacement events, we're going to have to grow this fault to 15 to 30 kilometres in length, and in that case it would have to extend offshore into Cook Strait. So frankly, we don't really know where the fault goes, but we believe that it's capable of earthquakes in the low 6s, potentially up to 7 if it's getting up towards that higher end. And to put that into perspective, when we look at those empirical relationships, we get recurrence intervals of the order of 2 to 7,000 years, which seems pretty okay with the observations we've made on the recurrence intervals at that level. In comparison with the major earthquake sources in Wellington, such as the Wellington Fault and the Hikurangi Subduction Zone, it's a smaller structure, and those other bigger faults have magnitudes probably in the range 7.5 to 8.5, with recurrence of about 1,000 years on those. Now, we made this information publicly available about 2 months ago, and it created a media storm. We worked closely with the regional and city councils in terms of developing material to present at a joint media briefing. It was highly publicised. There were many concerns about risks, building codes, implications for insurance, etc. What we told the public and the stakeholders was that the ground shaking hazard for this fault, although it's only newly discovered as being active, is already captured in the national model and therefore is already in the national building codes because of the background seismicity component of that model, which captured structures up to 7.2 capability. So it's not really a significant change in terms of ground shaking hazard for probabilistic assessment, but of course it would be a significant hazard in terms of local ground rupture, both onshore and offshore. And we were asked questions, will there be more? And of course the answer is probably yes. So my final statements to bring both of those study areas together are really just to bring us back to the fact that these are hidden faults, not previously recognised. They're low slip rate, less than 1 millimetre a year. They are significant. We've had devastating earthquakes on them. If we're lucky, we'll get an ability to look at slip rates through vertical displacement analyses on these kinds of structures, and that despite the fact that they're at this one's right in the heart of the plate boundary, but Canterbury's at the fringe of it, the complexity of the faulting is very important as seen by the Canterbury earthquake sequence in terms of stress interactions. Thank you very much.